Hello friends, I welcome you in lecture number 34 on higher order ODEs. In this lecture we are going to solve this differential equation, and this question was asked in GTU Summer 2019 exam. This differential equation is special type of differential equation. You can see that in every term the order of derivative and power of x are same. Here we have third order derivative, so power of x is 3. Similarly, with second order derivative, we have second power of x, and with zero derivative, we have 0 power of x, that is 1. So we know that if in every term order of derivative and power of x are same, then that type of equation is called Euler-Cauchy equation or Cauchy-Euler equation. And we can convert Cauchy-Euler equation into linear differential equation with constant coefficient by some substitution or some transformation. We have discussed about Cauchy-Euler equation in detail in earlier lectures, so if you have not seen those lectures, I suggest you to watch those lectures on Cauchy-Euler equation first and then go for this lecture. So because this is Cauchy-Euler equation, we have to consider some transformation, and using that transformation we can convert this equation number 1 into differential equation with constant coefficients. So we remember or we recall that here we have to change the independent variable x to new independent variable, say z, by the transformation x equal to e raised to z. Remember that whenever our differential equation is Cauchy-Euler equation, we will use this transformation x equal to e raised to z to convert given equation into differential equation with constant coefficients. In given equation we have two variables y and x. Y is dependent variable, x is independent variable, and we are changing the independent variable x to new independent variable z by this substitution or this transformation. And if I take log on both sides of this equation, I will have log x equal to log of e raised to z, that is z. Therefore I have z equal to log x. And we have already discussed in earlier lectures that if we use this transformation, then we have x into dy by dx. This is going to be dy by dz, and if we use d1 symbol for this derivative with respect to z, then this we can replace by d1y, that is x into dy by dx will be equal to d1y, where d1 is the derivative with respect to z. All these things I have discussed in earlier lectures on Euler-Cauchy equation, so you can refer those lectures to understand all these things. And this x square times second order derivative with respect to x will be replaced by d1 times d1 minus 1 times y, and third order derivative multiplied by x cube will be replaced by d1 times d1 minus 1 d1 minus 2 times y. And in general, if I have x raised to n times nth order derivative, then we will remember that it is replaced by d1 into d1 minus 1 into d1 minus 2 and so on d1 minus n minus 1. If we have n here, we will go up to n minus 1 and we will multiply all these things. So you can remember this, that whenever I have Euler-Cauchy equation, I will change the independent variable by the transformation x equal to e raised to z, and this type of terms will be replaced by this type of terms. And here y is y is a function of z. Whenever I am writing d1y, that means I am writing dy by dz, and on this side y is a function of x. Now once we have all these things converted in terms of y and z, we can substitute them into given equation, and we will see that given equation will be converted into differential equation in y and z, in which all the coefficients will be constants. So now I am using all these things into equation number 1. Using this in equation number 1, we have our first term is x cube into third order derivative with respect to y, that I will replace by this quantity d1 times d1 minus 1 times d1 minus 2 y. Second term is 2 times x square into d square y by dx square. X square into d square y by dx square will be replaced by d1 times d1 minus 1 into y plus 2 into y equal to x. So I keep 2y as it is, and x is replaced by e raised to z. Now in each of these terms y is common, so we can take y common, and simultaneously we can multiply these two. So we have d1 into d1 minus 2, that is d1 square, minus 2 d1 minus d1, that is minus 3 d1, and minus 1 into minus 2, that is plus 2, plus 2. I can multiply these two also. So I have d1 square minus d1 plus 2 and y common equal to e raised to z. Again I multiply each of these terms by d1, and I have d1 raised to 3 minus 3 times d1 square plus 2 times d1 plus 2 times d1 square minus 2 times d1 plus 2 y equal to e raised to z. And here we can see this 2 d1 will get cancelled, and we have d1 to the power 3 minus 3 d1 square plus d1 square, that is minus d1 square and plus 2 y equal to e raised to z. And this is a differential equation with constant coefficients in y and z, which is linear ordinary differential equation with constant coefficients in y and new independent variable z. Original equation was in terms of x and y, but it was not differential equation with constant coefficients in terms of x and y. Therefore we are changing the independent variable, and we find that differential equation reduces to differential equation with constant coefficients in y and z. And we know the methods of solving differential equation with constant coefficients. So using those methods we will obtain the solution in terms of y and z, and after we obtain this solution, we will replace this e raised to z by x or z by log x. So now we have to solve this equation number 2. So first we have to solve the equation which is homogeneous corresponding to this equation 2. So I am writing corresponding homogeneous equation. The corresponding homogeneous ordinary differential equation to equation number 2 is, we have to consider right hand side equal to 0, and we have d cube minus d1 square plus 2 y equal to 0, and the general solution of this equation will be complementary function of equation number 2. and here we will keep in mind that our independent variable is z. To solve this, I have to first write down the auxiliary equation. Auxiliary equation is written by replacing this derivative by lambda, that is we have lambda cube minus lambda square plus 2 equal to 0. Now to solve this auxiliary equation, first we have to obtain one value of lambda which satisfies this equation, and that value is divisor of constant term if it is integer. We know that integer solution of this type of equation is always divisor of constant term. So we can see that constant term is 2 and divisors of 2 are plus or minus 1 and plus or minus 2. So we can check by trial and error that which divisor out of these 4 will satisfy this equation. Suppose I take lambda equal to 1, then I will have 1 minus 1 plus 2 which is not equal to 0. Now I am taking lambda equal to minus 1, so minus 1 cube, that is minus 1, minus square of minus 1, that is 1, plus 2 equal to 0. This means lambda equal to minus 1 satisfies this equation. Therefore lambda equal to minus 1 is one solution of this auxiliary equation. Therefore one factor of this left hand side will be lambda plus 1, and in the bracket we will have polynomial of second degree that we have to obtain by using synthetic division. So if you recall, we are finding other two solutions in this way. One solution is lambda equal to minus 1. Here we are writing the coefficients of powers of lambda, and last is constant term. Coefficient of lambda cube is 1, coefficient of lambda square is minus 1. There is no term with lambda, so we write 0. Constant term is 2, and here we put 0. We add these 2 and multiply with this minus 1, that is minus 1. Again we add these 2, we have minus 2. Minus 2 into minus 1 is 2. 2 here, 2 into minus 1, minus 2, 0. This is starting with lambda cube, so this will start with lambda square, then lambda and constant. So coefficient of lambda square is 1. So here I am writing lambda square. Coefficient of lambda is minus 2, that is minus 2 lambda, and constant term is 2. So we have obtained these two factors. One is linear, another is quadratic. So therefore lambda plus 1 equal to 0, and lambda square minus 2 lambda plus 2 equal to 0. This will give me lambda equal to minus 1. To solve this, I can rewrite this as lambda square minus 2 lambda plus 1 equal to minus 1. I am breaking 2 as 1 plus 1. And here you can see we will have complex roots because b square minus 4ac is negative, and this I can rewrite as square of lambda minus 1 equal to I square. Minus 1 can be replaced by I square. Therefore lambda minus 1 equal to plus or minus I, taking square root on both sides. Therefore lambda equal to 1 plus or minus I. So these are two complex roots and there is one real root, and therefore the complementary function is corresponding to lambda equal to minus 1. We will write c1 e raised to minus z. Be careful here, our independent variable is z now, so we will not write c1 e raised to minus x, we will write c1 e raised to minus z. Similarly, to write down the part of complementary function corresponding to complex roots, what we are doing, we are comparing this with alpha plus or minus beta I, and we find that alpha and beta both are 1, and we know that the solution corresponding to complex root is e raised to alpha z cos beta z. Alpha is 1, that is e raised to z cos z, plus c2 e raised to alpha sin beta z. Alpha and beta both are 1, So we have e raised to z cos z and e raised to z sin z corresponding to these complex roots, and this is the complementary function of given non-homogeneous equation. Not given non-homogeneous equation, it is the complementary function of this equation number 2, which is linear differential equation with constant coefficients. Now to find out the particular solution or particular integral, we will use shortcut method. Here right hand side function is e raised to z, so shortcut method is applicable, and from this we will see that particular integral will be equal to 1 over this bracket d1 cube minus d1 square plus 2 applied to e raised to z. So now we obtain that second part of the solution, which is particular integral or particular solution. So the particular integral is, we can use this notation p dot I, or we can use y suffix p also. So yp equal to 1 over d1 cube minus d1 square, let me check here, d1 cube minus d1 square plus 2, and that we have to apply to e raised to z. And we know that if right hand side function is e raised to alpha z in shortcut methods, then we replace the derivative either d or d1 by this coefficient of z, that is alpha. Here coefficient of z is 1, so we have to replace d1 by coefficient of z is 1, therefore we have to replace d1 by 1, that is 1 minus 1 plus 2 e raised to z. What we have done, we have taken d1 equal to alpha, alpha is coefficient of z which is 1, and after putting d1 equal to alpha or 1, this is non-zero, therefore we have 1 by 2 times e raised to z as our particular solution or particular integral. And finally we write down the general solution. The general solution is nothing but addition of complementary function and particular integral, and therefore we have to write complementary function was c1 e raised to minus z plus c2 e raised to z cos z plus c3 e raised to z cos z sin z. This is sin z plus yp, which is 1 by 2 times e raised to z. So this is solution in terms of y and z, and our solution must be in terms of x and y, and we know that e raised to z is x and log x equal to z. So we will use these two, whatever is suitable. For c1 into e raised to minus z, e raised to minus z can be written as e raised to z to the power minus 1, e raised to z is x, so I will have x to the power minus 1 plus c2 times, I will replace e raised to z by x, and cos of z, z is nothing but log x. Similarly c3 times e raised to z, e raised to z is replaced by x, and in sin z, z is replaced by log x plus 1 by 2 into e raised to z, that is x. So this is the general solution of given Euler-Cauchy equation. If we wish, we can write in this form also, c1 divided by x plus c2x cos of log x plus c3x sin of log x plus x by 2, and here this c1, c2, c3 are arbitrary constants. So in this way we can easily solve Euler-Cauchy equations also by using the transformation x equal to e raised to z and by applying this type of shortcut methods if they are applicable. And this is very nice question. It was asked in GTU Summer 2019 exam. So this is all about this session. I hope you like it. Thanks for watching.